Hello everyone, my name is Ramnath Swami. I'm product manager for Mobile Studio. As part of product management, I'm also responsible for engagement with game studios and to bring great stories to developers like the one we have with King today. With me is Peter Ridgway, Senior Director from King. I'll now let Peter introduce himself briefly.
Thanks, Ramnath. I'm Pete Ridgway. I'm Senior Technical Art Director at King. I work across all the different projects in our new games portfolio, and I'm responsible for making sure that our content is efficient as possible, our artistic content, and also from a graphics point of view that we're rendering as efficiently as possible, and where possible using the most appropriate techniques to deliver high quality visuals at King.
Thanks, Pete. We are here to talk about the incredible journey that King and ARM took during the development of the mobile version of Crash Bandicoot on the Run. Right from the early stages of Crash Bandicoot development, performance was paramount for King. The attention that King paid to game optimization was very refreshing, and we at ARM are extremely glad and privileged for being part of that King's effort. Before I hand off to Pete, let me give you a brief overview about ARM and what we do. ARM designs CPUs and GPUs that are found in most mobile phones. 2020 is the fifth consecutive year that ARM has shipped over 1 billion Mali GPUs. So 5 billion Mali GPUs shipped in last 5 years. Hence, ARM has the expertise to help game studios with game optimization, and it is very much in our interest to make sure that your games run efficiently on our hardware. Hence, on top of hardware development, we also invest heavily on helping the developers as well. The way we do that is through our ARM Mobile Studio program. Although Mobile Studio is a tool suite that we offer to developers, the program itself has three parts to it. First is developer engagement. These engagements are usually tailored to specific needs of the game studios we engage with. Some of them like us to do game reviews, some ask us to handhold them with our tools when they get up to speed with them. Some customers have one-to-one Q&A sessions with us on various topics. The second is developer education. We continuously roll out educational contents for developers. They are related to a wide range of topics like graphics fundamentals, customer case studies, and tutorials to integrate our tools into your workflow. We ran a webinar series in May 2021, which was very well received. If you haven't had a chance to attend those webinars, you can view them on demand from our Mobile Studio developer page. Please do check that out, and there are a lot more useful contents in our developer pages. Empowering the developers with knowledge is one thing, but developers applying that knowledge on their daily work meant that Android graphics developers needed credible performance analysis tools that are easy to use. Hence, 2 years ago, ARM started heavily investing on Mobile Studio tool suite, and it is free to use. The best way to ensure that your games are optimized for Android is to have tool experts in your team. Hence, we help create power users of our tools in game studios. The way we do it is again fully tailored to the individual studios we engage with. Colleagues at King are great examples of such power users. And the journey we took with King on Crash Bandicoot is a perfect example of what ARM does. If you want to be a Mobile Studio expert, just get in touch with us via email. We can help. Before Pete talks about the great work they did at King, let me quickly introduce Mobile Studio. ARM Mobile Studio is a comprehensive set of tools for graphics optimization on Android. The suite contains various tools like Performance Advisor, which provides easy-to-read performance reports, Streamline, which is very detailed system profiler, Graphics Analyzer is an API tracer, and Mali Offline Compiler gives you compiled statistics. In the last 2 years, we have made our tools much easier to use, and we are glad to say that it is now starting to benefit big game studios like King and many others. Hence, more and more important game titles are being optimized for Mali GPU. Mobile Studio workflows are much improved now. Thanks to the new device manager, manual device connection is now plug and play, enabling users to start capturing performance data with just few clicks. Continuous integration is proving to be a powerful workflow as well, especially with the combination of our Performance Advisor tool. And we are supporting more and more Mali-based phones every day. On the analysis front, we have already automated a large chunk of manual triage work with the introduction of Performance Advisor. And the future looks even more exciting. More and more automation are on our roadmap. With that, I will now hand over to Peter Ridgway from King, who will talk about the development and porting of Crash Bandicoot to mobile. Over to you, Pete.
Thanks, Ramnath. So here at King, we're very well known for our existing franchises: Farm Heroes, Bubble Witch, Pet Rescue, and of course Candy Crush. Crash is a very different type of game for us, and it's also our first game featuring Activision IP. So Crash is what we call a hybrid game. At the core, it's a endless runner type of game, and it also features resource management. Basically, you will perform these runs, you will collect ingredients, you will then go back to your base, craft portal weapons from those ingredients, use those to fight bosses, to then progress to next levels and new worlds. When talking about Crash Bandicoot on the Run, we must recognise the significance of Crash as a franchise has had on gaming culture. The original Crash was launched in 1996 and was part of the initial PlayStation drive. Sony realised early on they didn't have anything to counter Nintendo with Mario and Sonic with Sega. So they kind of looked to Naughty Dog with their newfound character Crash Bandicoot to be the kind of face and one of the main faces of the PlayStation. As you can see from the images here, there's been numerous games afterwards. There's a massively loyal fan base around Crash. And when taking it to mobile, it was very important that we recognise and appreciate the passion of the fans and the kind of significance of this as a gaming icon. When we looked at our ambition for Crash, with the kind of concept images we had here, it was very clear we wanted to go for a more vibrant approach to the graphics. This was to complement the kind of form factor and the expectation of the audience. Being on a mobile phone, it's very different to that of a console. For one thing, our game was going to be played in a portrait view rather than widescreen view. And that was very important for how we looked at styling the graphics and what approaches we might take there, both aesthetically and artistically, as well as technically. One of the other differences we have on mobile compared to console is the number of performance considerations we have. On console, you have one or two main things you care about. It's memory. Does it fit on the game? Does the game run in memory at any given moment? And what's my frames per second? Am I running at 60 or 30 frames a second? When it comes to mobile, you have far more considerations. You have those previous to the memory and the performance, but also you have the over-the-air install. Will it install over the air? I have a 150 megabyte limit of installation size before I download any extra data. Can I fit within that? What disk space am I taking up on the device? On a mobile phone, you're always fighting against video, against music, against photos of everyone else's life on there. You also then have to look at the performance heuristics over time. So if you're running at 60 frames a second, that's great. But if you're using every available resource to do that, you're then going to start cooking the phone. It's going to start overheating. You're going to then start getting thermal throttling, where the device lowers its performance characteristics to compensate for the heat. You're also going to be draining the battery. Either one of those last two things is going to be a real impact on the player's user experience on the product. And that's not going to reflect very well on the game. When we look at devices we need to support, if you look at this graph here, the blue area represents the performance characteristics, the 3D mark performance of the majority of the devices out there. And as you can see, there's a big range of scale from the high end to the low end here of devices. When we looked at the early pre-registrations of the game and looked at our market segmentation and who our target audiences were and the devices they have, we kind of got this orange line there, the predicted player devices. And as you can see, this is very different from the performance curve. Because our game's free to play, we only monetize a small amount on the players. So we have to get this game into the hands of as many people as possible. We can't just target the very high-end powered devices. We have to look at getting a wider balance here. So if you look at the kind of range of devices we need to support, the performance multipliers on those devices is crazy. This is far more than people would normally be supporting on any form of console. Any form of Sony and Microsoft and Nintendo device power ratios are very much smaller than we see here in mobile. And obviously on all these devices, we want people to experience fantastic visuals. We want them to really have the same level of quality experience as possible. And as you can see on there as well, just I marked out the S8 for relevance. That's not an old phone, that's a really good phone as well. So this is, we're having to support devices quite far back or quite low in terms of performance. The first thing we had to do was to divide all of these devices into four main categories: high, medium, low and ultra low. From there, we tried to address the general performance heuristics of those types of devices. For example, the first thing we looked to address was the memory. On the low devices, we go down to support 1 gigabyte devices. That's really not much when you take into consideration the operating system, you take into consideration any fragmentation and other active applications in the background. So one of the things we did there was to quickly lower the texture resolutions down to half, down to a quarter size, and also disable anisotropic filtering on the very ultra low devices. That got us a good amount of the way. We also had to look at our streaming budgets and how we were kind of using that and bringing things in and bringing our streaming distances closer so we weren't overloading that part of the system. Next, we started looking at the CPU and GPU, where we tried to maintain 60 frames a second, but on the low-end devices, we dropped down to 30. We have now just done a release where we've actually moved the ultra-low up to 30 frames a second as well. But we then had to do things like removing objects, degrading the kind of shadow masks we were using, scaling the draw distance since we weren't drawing as far in the distance, and doing our horizon curvature closer. We also then on the GPU went heavily into optimizing the shader calculations. So we removed reflections, we brought in the LOD biases, we changed the resolution, so we lowered the resolution that we were rendering to before we're going presenting to the final frame. We do shader complexity, and we changed the reduction in LODs, so we didn't have the highest level of mesh possible, and we also simplified our skinning calculations on these low-end devices. When looking at the optimization, it was really important for us to try and simplify this process. You have kind of at the end phase of any product, you have two kind of main parts. You have the final push for the quality and the final optimizations of it. Now, we took the approach of it locking down on the graphical quality. We'd already set some pretty realistic budgets. We'd been optimizing as we'd been going, but then we focused on getting the art polished to the stage we wanted it, making sure the shaders were performing as nice as we wanted graphically, all the features were in, and the content was locked. From that point, we then started focusing on more optimizations and looking at what we could strip away. They're kind of diametrically opposed tactics on the diagram you can see here. You know, on one hand you're trying to improve quality, on the other hand you're trying to improve the optimization. If you try and do both at once, you're going to get into a very frustrating cycle of removing and adding, and no one's really clear on exactly the status you need to be at that moment in time and what's the driving factor. So we locked down the quality, then we went and focused on the optimization. The way I like to look at it is it's kind of like impressionism. You get the final picture there, the image you want, which is the reality, and then you're stripping back enough parts of it that it still feels the same, but it might not have all the details. You strip it back so the actual mood and vibrancy that you feel as a player playing the game looks and feels the same, where actually there's a few subtle details that if you went and did side-by-side comparisons, you'd actually notice the difference. But people aren't going to have the luxury of doing that. So that's the kind of approach. When it comes to content optimization, this was one of the first things we started to address once we'd locked down the content. We'd already set good budgets. We'd already set very realistic vertex targets there. But actually, when we started doing the performance and everything was brought together, we realized we were spending too much time on vertices. We were discarding a lot of the vertices. We were calculating the rendering of them and then discarding them through either micro triangles that didn't actually contribute to a pixel being rendered, or we were discarding them because they were backface called or off the screen. We went through the content, and actually it was a really important thing to do because we went through every single model and just stripped back down to the kind of bare essentials. Once we could see it in the context of the game and see it through multiple levels, we understood where we could make the changes. Things like these trees here, actually we could get 69% saving on the vertex count by going through and just adjusting the base mesh. We went through and tuned our level of detail toolings where we take the model and do multiple simple versions of it. We tuned that to be more aggressive and remove more micro triangles. We also combined many meshes together so we could reduce the draw calls, and actually at the same time in our LOD combiner tool, mesh combiner tool, we removed backface objects, backfaces off objects as well. So we didn't even have to calculate them on the device. And that in itself led to an extra 10% saving in discarded faces. So whilst we can do all the technical things in the world, we have to really look at content as well. Nowhere else would we be able to get this 30% reduction in vertex count if we didn't address this at the kind of artistic stage. The next kind of target we looked at was the actual shaders themselves. We started going through and we used the Mali offline compiler for this, which is a great tool where you can, from a command line, just compile your shaders, your fragment shaders and your vertex shaders, and see where you're spending your time. Is it going to be vertex bound, fragment bound, ALU logic bound, load store, everything like that. And what we started to see is actually we were our load stores were very high. Our ALU cost was going to be the bottleneck. So we started looking into this more, and we started to realize again we had stack spilling, where the computational cost of storing all the data from the logic in the shader was spilling out of the kind of memory onto the main memory. So we did some optimizations there. First off, we looked at the precision we were using, dropped the precision down to medium from high, and a few different things. We looked at the varyings we were passing from vertex shader to fragment shader and simplified those down as well. And this gave us some big savings, and this enabled us to prevent stack spilling, which again reduced our load store kind of activity significantly. A lot of this was done by simplifying our BRDF calculation. We'd gone very physically based initially, which was a good starting point for the artists. But as we started because we now had the content in there, we could actually look and go, we can simplify the shader logic here, because actually from an artistic point of view, we're not using the full range. We can quantize parts here. We can lose some of this, some of the aspects of the shading complexity here. And this is why, again, it's good if you can get your content into a stable place beforehand. You can do an optimization, pass on it beforehand. And then when you're doing things like this, you can validate it against a proper ground truth. And this also led us to do a really nice technique called tangent space lighting as well. So the idea here is, rather than normally with a kind of shader technique, you take your tangents and your normals and binormals and your lights, you make sure everything's in world space on the vertex shader, you transform those from the object space to vertex space to world space, and then you transfer that across the fragment shader, where you then would sample your normal map. You would then make up the matrices to the surface, and you would take that from tangent space on the normal map into world space and then calculate your lighting. We did a different way. We looked at that and we found that was quite expensive, and we can see here from the kind of graphs that if we took things like normalizing off, we would lose precision, we would lose accuracy in the surface results, and it was a bit of a saving. We lost some areas here, but we were able to get this further down with tangent space lighting. And the idea here is you actually take your lighting and you convert it into tangent space on the vertex shader. So you take your lighting calculation, which is your lighting direction in world space, you reconstitute an inverse matrix on your vertex shader to put the light into tangent space for that surface, and then you pass that data across into the fragment shader. There on the fragment shader, you can just sample your normal map, and that's it. You don't have to do the expensive matrix calculation or renormalization on the fragment shader. Now, if you see on the image on the bottom right, where we had normalized normal mapping, so the standard way of doing it, if that was your biggest cost, we were able to get it down to about 80% of the cost with using tangent space lighting. That actually, when we went down to no normal mapping, we actually realized the tangent space lighting was very similar in cost to there. So we were able to still maintain normal maps, but actually do it a slightly different way. And this was really important when we started looking at the kind of doing this extra optimization for the fragment shaders. From the graph at the top, our early utilization was 68.8%. That was very high, and we were seeing this consistently across the board. We were really hitting the fragment shade, and we needed to see these kind of reductions. And as you can see here, when we look at the kind of images side by side from the original to tangent space lighting, and then we have the kind of computational diff here, you can actually see that there's actually very little change. In terms of what your eye perceives, most people wouldn't be able to tell the difference between those two images in the center and the left. Now, the areas where we're seeing on here the biggest changes, this is something we didn't actually address at this moment, but the environment maps on these images was broken because of obviously now everything's in tangent space rather than world space, so we weren't reflecting the same part of the environment map. We later fixed this, so actually the metallic areas like the hanging brazier you see on the bottom, the actual difference there was far less than you see in this image. But for the most part, for the rest of the image, you really struggle to see. And this was a good saving. It actually equated real-world terms on a Samsung S6 to about 5 milliseconds from the GPU, which, that's a good saving in anyone's book. So after we'd optimized the tangent space lighting and got the fragment shader a bit more in order, we started looking at where else we were spending time. And we noticed that the render order was incorrect. So ideally what you want to render is front to back on the image. So you render close to you first, and then when you're drawing the next thing, it's already partially occluding that, so you don't play the fragment cost when you're excluding in depth those pixels behind there. We weren't doing that. We were rendering, as you can see here, the character, then the terrain, then the kind of shoulders, and then overlaying the objects on top. And this was leading to about actually 12.5% of the image being overdrawn when we could really easily avoid it. So we went and changed the render order, and we got this kind of working correctly, going front to back. So we did the objects on top of the terrain and things like that. And we tested it, and we didn't see any frames per second improvement, which was very disappointing. So we went into Streamline, which is another tool provided by ARM, which was great for getting us very detailed analytics of this. We looked there, and actually we found that, yes, we weren't seeing any frames per second at that moment in time, but what we were seeing was actually our memory reads were a lot, far greatly reduced. We were seeing about 5 to 10% savings on the load, the read and write stores, which was great. And this, whilst it didn't save anything directly at that moment, this led obviously to less battery usage, less bandwidth being used, and it actually led to less heat saving. So on some devices where we were starting to get thermal throttling after a few minutes of gameplay, this kind of change helped us avoid some of those kind of issues and prolong the play experience, which was great. And this is a case of sometimes you have to be very analytical with the work you're doing and really use tools like Streamline to understand all the implications. Whilst this didn't save anything immediately, over a long-term play session and battery drain and things like that, this was a very important thing for us to do and get right. Another important thing which helped us save a lot of bandwidth was IDVS. So this is index-driven vertex shading. This is a new thing that's kind of coming through, which is really, really helpful. On mobile, the way the tile-based rendering works is obviously you have to sample all of the vertices on the mesh to know which triangles belong to which kind of buckets and which tiles. Now, traditionally, what you normally do is you have for each vertex, you store the position, the tangent, the normal, and the coordinates, the texture coordinates. And then you do that for vertex 1, vertex 2, vertex 3, and so forth. That's great, but the problem is your load efficiency and your caching isn't as good as it could be. One of the things we did and worked with ARM on, and Pete Harris was very good at helping guide us on this, is we separated these into two buffers. So as you can see here, the top buffer is the original buffer with the position, tangent, normal, and texture coordinates stored. And then the bottom one, we actually split into two vertex buffers. One for just the positions, and then a second one for the tangent, normal, and texture coordinates. This was great because when it comes to the tiler, it could just look at position, 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 and just read straight through the buffer sequentially rather than having to break and skip ahead. So this gave us some really good improvements. As you see there in the table at the bottom, the load store level 2, we had 11% gain. DRAM read was 14% gain. The full total read saving was around 3 times the difference. And this was great. This was something that really helped us save on the thermal throttling. Some of those devices that after 5 minutes started to get a bit warm and then started to, depending on the situation, how they were being held in people's hands, started to slow down, and then we'd see frame rate issues. This really did help us take that out of the equation so that they were stable all the way through. It was a great saving, and this was a really good benefit of our close collaboration with ARM that we came about getting this and implementing it. And it really did help save the bandwidth and thermal impact of the game. Next things we looked at, or I'll talk about, is blue noise crossfading. So traditionally, when you have levels of detail, you will just swap between one to the next to the next. So you have your highest detail model, your next level of simplicity, and then your final level of simplicity. This is great, but the problem here is this always results in some form of popping. As that switch happens, you see a change in the geometry, a change in the silhouette, or the textures move slightly. The problem here is, as humans, we are accustomed to looking out for these changes. Anything that has a quick kind of movement or change like this, our eye automatically darts towards. It's basically primal survival instinct. If something moves in a bush, you notice it. It stands out to you. You see things out the corner of your eye, and your eye automatically goes, "What's that? I'm going to move to it." This is really bad when you're doing something like a runner game or a kind of precision-based game like this, where you need the player to focus on the actual track and what's going on there, not the background items around it. So one of the things we did is we invested in looking at blue noise crossfading. So the idea here is you use a blue noise dithered pattern, and you quickly, over a small distance and time, you transition between the two levels of detail. You can see here on the video as we kind of move back, the camera moves backwards and forwards, the quick fade over there, and you can see the kind of dithering pattern go on. But this kind of makes it look more like there's a soft transition when actually there isn't any soft alpha going on here. This is pure dithered noise on-off pixels going through. We looked into Streamline to quantify this because it was adding extra complexity, But when we went through with Streamline and Profile it in numerous devices, what we actually found was the cost increase was absolutely negligible. There was hardly any kind of gain we were getting from this in terms of our render performance, in terms of cost. So that was a really good sign for us. The great thing here is by adding this, it meant we could bring in all the levels of detail far closer to the player. We could transition to a lower LOD very quickly. And actually, we by doing this, we were saving significant amounts of vertex data every single frame. We were I think about 1/3 our distance of LOD detail we were having to draw out to. So this was very good. And also it meant that we weren't seeing any pop whatsoever. So actually aesthetically and quality-wise, it felt more solid. The world felt good because there was a lack of pop and things distracting your eye and attention. So I think to kind of sum up a couple of the key takeaways here. One, mobile performance is far more complicated than PC and console. The number of variables you have to deal with, the kind of device profiles, the hardware itself, all of the other complications of memory, load, thermal throttling, things like that, means it's so much more complicated than your standard PC tuning or console tuning of a game. You really do have to think strategically about your performance. You can't leave anything unturned. You have to expose every single thing, even if it doesn't give frames per second back. It's worth doing if it saves bandwidth, if it saves any form of consumption at all. You have to really look at these things and leave no stone unturned. Also, there's never a silver bullet. There's never we can do this one thing that will drastically save us. We had a combination of things, far more things than we've actually got detailed in this presentation. You always have to go through, look again. We went through numerous times revisiting the content, making sure we were making everything as efficient as possible. From a memory point of view, from a rendering performance point of view, we built up kind of automated testing stations to go through and constantly run the game and check that we weren't degrading the performance anywhere. You also need to make use of all the tools. ARM were fantastic helping us. They came and gave a couple of training sessions on how to use the different tools and things to look out for, which was invaluable to the team. Pete Harris, call out to him especially for his training session he did, which was excellent. We spent a lot of time using the Mali offline compiler and the Streamline tools to identify these problems. We made a lot of assumptions. Most of them were pretty accurate, but some of them we were off. And we wouldn't have really understood that and the reasons why we were off unless we'd been using things like Streamline to identify these issues. It really did save us on a few occasions. It helped us identify these bottlenecks and make sure that we were always working towards the most important thing at that time. And again, I'd just like to shout out the engagement with ARM. The great workshops they kind of held, the reviews of the game, providing us feedback was fantastic. And having that kind of level of expertise at the hardware level, able to feedback on our game, was invaluable for the launch of the title.
Thanks, Pete. It is impressive to see that you think about performance not just from FPS perspective, but also beyond that. I'm sure your work on Crash Bandicoot gives great insight for those who are going to be optimizing for Mali. Now, for my part, let me give you something to take away from this talk. If you haven't heard about it earlier, ARM is running an optimization competition for eligible developers. There are attractive prizes lined up for winners, and ARM will further give the winners credit for their achievements by promoting them across various marketing channels. So please do get in touch with us for more information, either about the competition or about the longer-term engagement I talked about earlier. Best wishes from King and ARM for your graphics optimization.